going to take a look at 4 theorems and start to get an idea of where this is all taking us. So the first two we're going to talk about is the remainder theorem and the factor theorem. The remainder theorem is, and we're going to use a lot of synthetic division because the remainder theorem deals with a linear binomial, x minus k. And it's basically saying that if you divide any polynomial, and you can always do this, you can always divide by a linear binomial, the remainder will be f of k. Basically, when I put that k back in, out will come the remainder. That can come in handy in a lot of different scenarios. The next one is the factor theorem. If x minus k is a factor, again, a linear binomial, and we can always divide that into a polynomial of a higher degree, and it comes out to be 0, then that is a factor. This is going to be pretty big in what we're going to do. I'll show you. I have an example for each. So let's go ahead and do the first one on the remainder theorem. So the first thing I'm going to do is I got my f of 2, so basically we're looking at x minus 2 as my factor that we're going to divide into. And I could do this by long division, absolutely. But let's go ahead and use synthetic. A little easy and a little quick. I first check to make sure my polynomial doesn't have any gaps in it, and this one doesn't, so I'm going to write my leading coefficients. Draw my line. I'm going to drop my negative 3. 2 times negative 3 is a negative 6. Add, I get a negative 1. 2 times negative 1 is a negative 2. Add, I get a negative 3. So I basically have a negative 3x minus 1 with a remainder of negative 3. So if I did f of 2, I know I'll get a negative 3. Of course, I could have done it the long ways, but keep in mind that very often we're going to have some ugly polynomials, 5th, 6th power sometimes, and we may want to find what f of something is. And this is another way to check if we have a factor or not as well. So certainly I could have done this. I could have done negative 3 times 2 squared, all right, plus 5 times 2 minus 1. And that's going to be 4, negative 12, 10, 3. That gives me a negative 3. Let's go ahead and take a look at the factor theorem. So the factor theorem, we're looking to see if our remainder is going to be 0. So again, I'll use synthetic real quick, and this is x plus 5. Remember, x minus k. So we're going to have a negative 5 here. And 3, 2, 1, 0, so we're all good. So I'm going to go ahead and write my coefficients. Okay. Drop the 1. Negative 5 times 1 is negative 5. Add, I get another 1. And I'm going to get a negative 5 times 1 gives me a negative 5. I'm going to get a negative 6. And negative 5 times negative 6 is a positive 30. When I add, I get a 0. So absolutely, this is a factor. Okay? Now it says list real roots. So what we want to do is, well, we have, basically we have x plus 5 as one of our factors. And then we're going to have, remember, this is a cube, so this is going to be x squared. So we're going to have x squared plus x minus 6 as our other factor. This is factorable. So what times what is equal to negative 6 when added together gives you a positive 1? Well, that's going to be 3 and 2, and 3 gets the bigger term. So I have x plus 5, x plus 3, and x minus 2. All right? So my zeros are x is equal to negative 5, x is equal to negative 3, and x is equal to a positive 2. Those are my zeros. And guess what we could do? We can plot these and sketch the graph and so on. Alrighty, let's take a look at this. Okay, now, polynomial remainder and factor polynomial, didn't we just do this one? Yes, we did. I don't know why I have it twice. Okay, this one. Alrighty, it is still July, so my brain is not up to speed on math. So what we're going to do is we're going to go ahead and do this one, but we're looking for what value of k is to give it evenly to a numerator. We're looking for the, basically the factor theorem. So I'm going to go ahead, my k, my divisor, I'm going to do 5. Alrighty. And I got 1, yep, all good. So I got 1, 4, negative 3, and k. I'm going to drop that 1 and call that a 1. So 5 times that is going to be 5. All right. That added together gives me a 9. Well, that gives me a pretty big number. That's going to be 45 when I multiply. When I add, that drops it down to 42. All right? So 5 times 42, that's going to be 200 plus 10, so 210. All right? I need to get a 0 right here. This has to be 0. Well, the only way for that to happen is if this is a negative 210. All right? So we found k must equal to negative 210 for this to be an even factor. Alrighty, I think, nope, I got some more stuff. Boy, am I just off in La La Land. Alrighty, so here's the last two theorems I was going to talk about. Number of zeros theorem, this tied into the fundamental theorem of algebra. Polynomial of degree n has at most n distinct zeros. And we're talking about zeros. Remember, when we graph, we're talking about when they cross the x-axis. Okay, we have so many distinct zeros. It doesn't always have to be that way. We can have complex roots. Remember, when we have a quadratic, we can have one solution, two solutions, or no solution in the real number system. But we'll always have two solutions for all these scenarios in the complex number system. So this leads us to our conjugate zeros theorem. If one of the zeros of the polynomial, say like over here, is a complex number, a plus bi, then a minus bi is another zero. They come in pairs, conjugate pairs. So if 5 minus 4i is a 0, then 5 plus 4i will be a 0. And we can use this to actually write polynomials of the lowest degree. There could be higher degree ones with these answers. And this gets rather interesting. So we're given the zeros of these right here. So we know that can be x minus 3. So let's go ahead and write our polynomial in factored form. Now keep in mind, we can have a scalar here. We're going to have an a up front. We don't know what that is. Our first zero, let's go ahead and call that x equals 0. So I'm going to call that x. All right. Our next one is x is equal to 3, so that's going to be x minus 3. Then I'm going to have x minus 2i as our next one. That's supposed to be an I. And this comes in pairs. If you have x minus 2i, you got to have an x plus 2i. All right, you got to have that. All right. So what we want to do is we basically want to solve for a, to write our function. So I'm going to rewrite this as f of x is equal to ax. There's my x minus 3. I'm going to clean up this conjugate right here. We've already practiced this in a previous lesson. So I do x squared, those cancel out, and then negative 2i plus 2i. This is going to give me a plus 4 because don't forget that I squared is negative 1. All right, so I'm going to rewrite this as x squared plus 4. All right. Now, key information right here. F of 2 is equal to 8. I'm going to put in 2 for all my x's, put in 8 for my y. I'm going to solve for a. That's going to be a 2. All right. That's going to be 2 minus 3. And that's going to be 2 squared plus 4. All righty. And then once I start knocking this out, I'm going to get negative 16 over here, by the way. All right. So I'm going to have 8 is equal to, because 2, 1, and then 8. 2 times 8 is 16. So I have 8 is equal to negative 16a. Therefore, a is equal to negative 1/2. And my final answer is this. F of x is equal to negative 1/2. And I could have multiplied these out if I wanted to. X, I didn't have to put that in parentheses, x minus 3, and x squared plus 4. This goes back into something earlier I said, that a polynomial, a higher degree polynomial, can always be can always be factored by a linear and its quadratics, but the quadratics may not be reducible. All right, so we're talking about the fundamental theorem of algebra here. Okay, so I'm going to leave you with this and go ahead and get this posted and make sure that you practice this stuff, because you know that's the nature of math. You have to practice it. It's a different part of the brain. Okay.